Thank you for the introduction. I'm Xiao Zhang from Hopkins. Today I'm going to talk about a new way to extract information from a field and about its application in cosmology. So when talking about the field, the first thing come up into mind might be the power spectrum. But as you know and introduced previously, the power spectrum does not have the ability to distinguish these two panels because they have the same power spectrum but look very differently. So in order to quantify the difference, we need a statistic beyond the power spectrum. So the traditional way to go beyond the power spectrum is by taking high order statistics or endpoint function. It's kind of multiplying together many field variables and then take the mean. So though it works very well in a weakly non-Gaussian regime, actually in extremely highly non-Gaussian regime, it has a number of limitations. The first, it actually, to the surprise of many cosmologists, it actually loses information in highly non-Gaussian regime. So here's a plot showing how it's the case. So even if the x-axis here is the non-Gaussianity of a log normal distribution, and the y-axis is how the fraction of information you can extract by using some particular statistic. And as you can see, when you go to highly non-Gaussian regime, actually, even if you use all the high order moments, you cannot extract all the information, and it can fail completely. This is shown by Zhu and Kaon about 10 years ago. So another problem of high order statistic endpoint function is that the number of coefficients increase very quickly with the number of points. So that means it becomes extremely difficult when you go to higher orders. In the recent years, we've witnessed the rising of a brand new approach with a convolutional neural net to extract information from a field. But although it is successful in many disciplines, it also has a problem. Mainly, it lacks transparency and interpretability. And it looks like a black box because we really don't know what it learned from the data. So the problem is, can we combine the advantage of these two approaches? And that's what exactly mathematicians did about 10 years ago to develop the scattering transform. The scattering transform is a statistic borrowing ideas from convolutional neural net. It kind of uses some mathematics we can find in convolutional neural net, but itself is just a process to generate summary statistics. So at the beginning, I would like to show you some visualization to demonstrate its power. The idea is to use image synthesis. So from the input field here, we can calculate particular summary statistics. And then we randomly generate new images with the same summary statistics. And we see whether the generated image have the same texture, visual texture, as the input field. So if we do it with the power spectrum, as expected, we'll get basically Gaussian textures, which is different from the input. And if we add the bispectrum constraint, it's improved, but still very far from the input. And by the way, I guess this is the first time many of you have seen the visualization of a bispectrum, what bispectrum see in the cosmological context. So for comparison, if you use the scattering statistic, basically you can generate the texture of the lensing mass map quite well. So we did play this trick for a variety of many different physical fields, including like Joule pattern or a turbulence field, and constantly we find a very satisfactory result. I think this strongly suggests that the scattering statistic have the ability to characterize the non-Gaussian textures found in physical fields. So when shown this high performance, I'm now going to talk about some details about the definition of the scattering transform. From the input field, we first pick a scale. by convolving it with a kernel or with a wavelet. And then so it's actually defined in real space. So they talk about convolutions. And then we take the modulus of the convolved field. So the purpose to do this is to convert fluctuations into the local strength of fluctuations. And I would like to draw your attention that the power spectrum actually can be defined in a similar way in real space. So it's there. So the only difference is we need to change the kernel into a local kernel in scattering transform, and we drop the square defined in the power spectrum. So the purpose to do these two modification is that then we can go to the next layer easily. So then, for example, if you don't use the local kernel, then the next layer will be not informative. And if you keep the square, then the next layer will be a fourth order, will be a high order statistic. But if you drop that, the square will always keep proportional to the field intensity itself. And finally, to construct translation invariant coefficients or statistic, you can just simply take the spatial average, or in CNN is called global pooling. So they are defined as the zeroth order, first order, and the second order scattering statistic or scattering transform, scattering coefficients. And of course, at each layer, we can have a variety of scales. So then it will lead to a tree structure of the scattering transform, which kind of resembles the network structure of convolutional neural net. But the difference here is that the scattering transform use a preset library of kernels, which are wavelet. It is not learned from data. So that's why the scattering transform is not a black box. So I think perhaps I'll not have time to go to detail of this. This is just some interpretation of the scattering transform. Is actually can be interpreted just as a low order endpoint function binned by wavelets. So I would like to draw your attention about some very interesting visual interpretation of the second order scattering coefficients, which are about non-Gaussianity. So some of them actually correspond to the structure sparsity in the field, and some others correspond to the shape of the structures in the field, like whether it's curvy or whether it's straight. So given this simplicity and great power of the scattering transform, we apply it to weak lensing cosmology. So the task here is we want to infer cosmological parameters from the statistical properties, right, of the lensing mass map. And we compare the performance, how well some statistic can constrain the cosmological parameter by calculating the Fisher information using a set of simulations generously provided by the Columbia Lensing Group. And here is, if you use the power spectrum alone, there's a well-known degeneracy between the omega matter and sigma 8 parameters. Basically, the power spectrum constrain this direction well, but not this direction, because this direction is about how deeply go into the non-Gaussian, the nonlinear regime. So the scattering transform basically can improve this constraint by an order of magnitude. It's like this. So this is, I forgot to say, this is in the noiseless case. And this is the composition of the contribution of different coefficients. If you ask, what about the bispectrum constraint? It's actually here. You see, it's of course an improvement, but it's much worse, I think, than the scattering constraint. And what's more is usually for bispectrum, you need more coefficients than the scattering statistics. So in the noisy case, we kind of find very similar results. Here, the plot x-axis noise level, decreasing noise. The y-axis is the constraining power. So first thing is that even in this noisy realistic case, there are still substantial non-Gaussian information in the lensing mass map. And then if I ask where is the scattering transform, it's here. So it's almost always following the performance of a state-of-the-art convolutional neural net. So I think this suggests that perhaps the scattering transform have exhausted all the available information in the weak lensing context. And in order to achieve this performance, you really just need to add about 40 numbers into the set of summary statistics. So this, again, usually much lower than that of bispectrum, and not to say the millions of parameters to be trained in the convolutional neural net. And we tested for other cosmological parameters and found similar results. Now we're working on applying it to real data, so it's not just theoretical, and the result actually will be published in the near future. And I'm also working on testing it in the Euclid collaboration. So it's really, so although the scattering transform have already 10 years old, actually it just started its journey in cosmology and physics. So to summarize, the main attractive advantage of the scattering transform is that first it's informative, it can reach CNN level performance. And second, it's very easy to use. It's almost like a power spectrum, and its set is compact and it's robust. It does not have the the tail and robustness problem as higher order statistics. And also, it is interpretable. So I would like to briefly go back to this plot showing the failure of higher order statistics. The reason is because higher order statistics probe the tail of a distribution by stretching it. So when the distribution have a heavy tail or long tail, you have the risk of divergence. And even if it does not diverge, you still can lose information. So the scattering approach is something like folding the core of the PDF in order to downweight the core and probe the tail. So they're doing the same thing, but in different ways. But by keeping first order and the scattering statistic can really recover a lot of information in the highly non-Gaussian regime. Okay, to summarize, I talked about different ways to extract information from a field. In particular, I talked about the scattering transform, which kind of a new approach sitting in between of the power spectrum and the convolutional neural net. So in one hand, it can be understood as a lower order endpoint function and binned by wavelets. And on the other hand, it can be seen as a mini CNN with preset kernels and without a need of tuning or training. So I've showed that the scattering transform performs quite well in the weak lensing cosmology, and it reached CNN level performance. And why is that? Why it can perform so well? I think the reason is because that in our physical world, most of the field we encounter in the physical world actually have a complexity in between the simple Gaussian random fields and the complex biological world. So then I would also argue that to extract information from all these physical fields, actually the scattering transform, which sits in between of these two approaches, is the way to go. Thank you.
Questions for Siha?
Could you go back, elaborate a little bit more on the tail of the distribution with the
yes, of course.
Higher order statistics?
Right. So so this is an experiment on a single variable case. So we have one variable which is log normal, follow log normal distribution, and the x-axis are for distribution log normal distributions with different non-Gaussianity, because in log normal you have one parameter changing the non-Gaussianity. When it's small, it's almost a Gaussian. When it's high, it's long-tailed. So then the y-axis here is showing if the amount of feature information contained in all higher order statistics what's a fraction of that as the Fisher information contained in the distribution itself. So in the non-Gaussian weakly non-Gaussian regime, that's what usually people believe. If you have all higher order statistics, you can finally recover all information. But when you go to highly non-Gaussian regime, actually that does not hold. So this is something actually well known for mathematicians called the moment problem. But for a while, many cosmologists believe, don't believe. It's just 10 years ago it's pointed out.
Thanks.
I think Sultan had a question.
Yes, very nice. So I wanted to ask about the interpretation. Did you make any effort about like, could you make the connection between the different angles and the different scales you use in your wavelet generation with the parameters, like with omega matter or sigma 8 or other parameters you look at? Could you tie them?
Yeah, so what we found is that for the cosmology case, so the plot here, the left is about the sparsity as a function of scale. The right is about actually the angular dependence. And what we found in cosmology is that it seems in weak lensing, at least, the right is not informative. So the angle of the shape of the texture does not have cosmological dependence. So mainly what is constraining is just the sparsity of the field. So coming back to this plot, again, is along this direction, it's basically the amplitude of the power spectrum. And along this direction, it's about how deep you go to the nonlinear regime. And you have this degeneracy because weak lensing is not directly measure the delta, right? It's measuring some projected quantity.
Okay.
Can you hear?
Yes.
Can you say something about how you picked these wavelet functions and whether they matter?
Oh yes, of course.
Did you try many different ones before?
Yeah, that's a very good question. So it's about the choice of kernels wavelet. So I think we've done some experiment, and it turns out that it does not influence the result very much. It's because actually almost all the wavelet is some bandpass filter in Fourier space. So though they can look different, but the idea is that you have a range of scales in Fourier space selected by the wavelet. So the commonly used kernels in scattering transform is so-called Molet wavelet, which is just a Gaussian in both real space and Fourier space. Right, but we do test others. It does not change it very much, although, so for example, if you use just step functions in Fourier space, the performance actually deteriorate. It's worse. Yeah, but it's not very much. It's about like a factor of, I think, 0.7%. So it might be an interesting question of how to optimize the kernel shape in the cosmological context, but we haven't done that yet.
Colin.
Yeah, thanks. This is interesting. I had a few questions. So first, do you apply any smoothing to the simulated maps before you apply the scattering transform? Do you have a sense of how your results look as a function of the smoothing scale that's applied?
Yes, that's a good question. So we did the smoothing for the lensing map. We chose it to be 1 arc minute in this case. So if you change the smoothing scale, of course you lose information at small scales. So one, I think, attractive property of the scattering transform is that it's actually still defined in terms of scales. So because we know if you smooth it, basically you remove the high K information. And that's kind of equivalent to abandoning the scattering coefficients corresponding to high K.
Right. Yeah. I mean, the reason I ask is that in a real weak lensing analysis, you don't want to naively include the information on small scales because we think it's contaminated by things like baryonic feedback physics, which presumably you're aware of if you're applying it to real data. So do you have a sense of, at what point, at what level of smoothing would your constraints sort of get back to looking like the power spectrum constraints? I mean, at some point, eventually, if you smooth the map enough, it will start to just look like the power spectrum, because on the linear regime, we know the power spectrum contains all the information.
Yes, that's right. So I think we haven't done the test explicitly, but I can imagine what you said.
It'd be interesting to know what scale that happens at.
I see. Yeah, that's a good suggestion. Thanks.
I guess then my final question is just, this is actually the plot I was interested in. So you have the comparison of this to the case of power spectrum plus bispectrum. But if I understand the rough cartoon level, I don't know, understanding what the S0 plus S1 plus S2 correspond to, wouldn't a more fair comparison be to the PDF plus the power spectrum plus the trispectrum, since it was roughly the mean P of K and then P of K of P of K?
Yeah, yes and no. Right. So yeah, so the S0 is the mean, and the S1 is some low order power spectrum, and S2 is some low order trispectrum, and in some manner. And that's correct.
Yeah.
But because of the effect I introduced about the high order statistic, actually lowering the order, the power of the statistic, it really can help you to gain more information in terms of the higher order information.
All right. Yeah, I just meant sort of
the spatial configuration arrangement is kind of similar to.
Right. I didn't mean that it should be exactly equivalent by any means. I just thought it might be a more sort of like apples to apples comparison.
Yeah, I think the apple here we are using is the number of coefficients.
Oh, okay. Okay.
As we know, if you go to trispectrum, the number of coefficients will be much more.
Yeah. All right. Thanks.
Any questions from the online audience? Okay. If not, let's thank Xiao again and Kate. Kate is going next. Kate Story-Fisher, who will talk about emulation of summary statistics for cosmology from galaxy surveys.
Hi everyone, my name is Kate Story-Fisher. I'm a PhD candidate at NYU, and I'll be talking about work I've been doing with Professor Jeremy Tinker there on emulation of summary statistics for cosmology from galaxy surveys. Okay, so this work is part of the Emulation project, which is a collaboration with folks from Stanford and other places around the country. So the idea is to extract more information from small scales in particular, which we think contains more cosmological information within galaxy surveys. But as you all know, cosmological simulations, which are the best at modeling these small scales, are very expensive. So the approach that the Emulation collaboration is taking is to use a very sparse suite of high-res n-body simulations to span the parameter space of interest in terms of both cosmological parameters and galaxy bias parameters, and then use the emulator approach to compute summary statistics of these and then extract that cosmological information back. And I'll be talking about kind of a specific project within this broader approach. Oh, and sorry, you can see here a slice of one of the n-body simulations. So you can see it modeling all of the scales. And for details, you can go to DeRose 2018. So I know in the previous session, Colin and Simone talked about emulation as, is it real ML, especially using probabilistic machine learning like Gaussian processes, which we do. I'll argue that it is, or it's close enough and it works for our purposes. But I'll note that we're also using other machine learning techniques or testing them in contrast to Gaussian processes to see if neural nets help better. But okay, so overall, the emulation approach is to first generate a bunch of simulations that span your prior space of both cosmological and galaxy bias parameters, and then to compute all of these summary statistics, as I said, to build up this training set. And I'll get more into the details of that set later. Then we train this Gaussian process to learn that correlation between the input parameters and the output statistics, and then use MCMC in this case to recover those parameters for our test set. So I'll go into detail about each of these steps. So we use the Emulation suite of simulations, which incorporates a 7-dimensional cosmological model and an 11-dimensional HOD model. And that includes, HOD is the halo occupation distribution, which is a way of modeling where galaxies fall within halos and the bias between the two. And this also includes 3 assembly bias parameters, which was referred to earlier in various talks about the dependence of where galaxies fall within halos on properties other than the halo mass. So in this case, we're going to consider the local density. And so our training set it consists of 40 cosmologies, and we populate those with 100 different HODs each. So that's 4,000 mock training set. And you can see in the black points how they fall across our cosmological parameters. And then we have a test set with only 7 cosmologies, but 5 realizations each, so we can get a handle on sample variance. And so that's 700 total mock catalogs for the test set. So the standard summary statistics that are often used for this purpose are the projected correlation function, WP of RP, which here on the left, you can see the 1 halo and 2 halo term pretty clearly if you're familiar with that. So this is just an example from one of our models that I've computed. And then on the right, we have the monopole of the correlation function, which is Fourier transform of the power spectrum. So these are the ones that are typically used. And we can train our Gaussian process emulators on these statistics. So for those of you not familiar with Gaussian processes, these are basically use a probability distribution over all possible functions that fit our data, of course, constrained somehow here by a kernel function that we choose. But basically, we can think of it as a fancy interpolator, like we can think of a lot of machine learning models that we were saying earlier, as just a mapping of our inputs to our outputs to try to interpolate that parameter space. So we spent a lot of time tuning our Gaussian processes, the choice of kernel, the scaling of our data, which do make a big difference. And we can see here how we train it with the input training set and the known parameters, and then we can apply it to our test set. So here is how we did. So we have the projected correlation function on the left and the monopole on the right. On the top, the lines are the emulator predictions running mostly through the truth values, which are the open circles. And then in the middle, we have that fractional error between the truth and the prediction. So you can see we're at around kind of max 10% error, usually less than that in each bin. And so we train this on 9 bins of each of these statistics. And then on the bottom, we can see that kind of overall error in each of the bins compared to the sample variance. So we can see that for WP, we get down to about 2% error, which is quite good for what's usually kind of what's known as about a few percent error in the theory on these, or about 1% error. And then not quite as good, around 5% for the monopole, but we get down to 2% at certain scales. So the idea of my project is to go beyond these standard summary statistics and look at other statistics, but that are still interpretable, and we might be able to understand kind of what information they're adding. So this is somewhere in between. It's a lot easier to compute than like higher order statistics like the bispectrum and trispectrum, and it's more interpretable than neural network compression techniques. So these are kind of using known statistics in the literature that are known to give us improvements on both cosmology in the case of the marked correlation function. It's known to improve sigma 8 constraints, and the underdensity probability function, it's known to improve HOD and assembly bias parameters. Briefly, the UPF, you can think of it just throwing down randomly placed spheres in your simulation and counting up the number density, and it's a function of the how many spheres are underdense as a function of the scale of the sphere. Where the marked correlation function is the monopole just weighted by the local density, which we compute as a number density in a sphere of 10 megaparsecs. And I have little kind of notes about the shapes of these, but so they actually are helping us probe the local density in the regions and different kind of populations of galaxies. But you can think of it as just new statistics that we're throwing into our emulator approach in order to improve our constraints. And so our emulators, I should say down here, we have the how well they perform. And we get down to quite good error for the UPF and still very good error for the marked correlation function, comparable to the projected correlation function. So here's a quick summary of some of our initial results. So I'm just showing for a single test model or test simulation how we do on recovery tests when we use our emulators in MCMC, which is obviously much faster than having to run a new simulation at every point, which is untenable. So on the left, we have a few cosmological parameters that we're sampling and the constraints just from WP. In the middle, we have a few of our HOD parameters. And on the right, we have all three of our assembly bias parameters. So you can see that even with just WPRP, we can get a little bit of constraints, but it's actually fairly close to our training prior. So we're not actually getting too much information from this standard statistic. But when we add in the UPF and the marked correlation function as additional observables, we improve the constraint significantly on some of these. So not too much with the cosmology, maybe a little bit on sigma 8 as expected with the marked correlation function, although we have a very slight bias for this particular model. In terms of the HOD, we get significant improvement. So we can see that the UPF significantly constrains the velocity bias. That's VBS, is the velocity bias of satellite galaxies. And then the marked correlation function significantly improves our constraints on MSAT, which controls the minimum halo mass at which satellites populate dark matter halos. And then in terms of assembly bias, we also see significant improvement, particularly from the UPF. And so this is really interesting to know how exactly these kind of void statistics and local density statistics are going to help us particularly constrain density-based assembly bias. And so this, of course, was just one test simulation. This is with a little sub-suite of 21 recovery tests. And right now, these still take a while to run, even with the emulator. So this is results in progress. But so far, I'm comparing WP to our full chains with the projected correlation function, the monopole, the UPF, and the marked correlation function in the dark blue. And these are cumulative histograms. And so if just to explain how these work exactly, if we had a perfectly peaked Gaussian around the mean, we would have a low line and then a step function along that black line and then across the top. And so you can see we're getting tighter constraints closer to that nice step function with the full chains significantly compared to just using the projected correlation function as the standard statistic. And so we're currently kind of running more combinations of these observables to understand exactly where this information is coming from. But with these tests, we can see that we're getting a lot of useful information from these non-standard statistics that probe the local environment. All right, so in summary, we train Gaussian process emulators that can emulate summary statistics from our suite of AMULA simulations at the few % level. We're working on comparing that to neural network emulators and other types to see if we can improve the speed and accuracy there. And the nice thing about Gaussian processes is we can also incorporate the uncertainty, which is really useful for analyzing our results. And finally, the emulators of both the UPF and the marked correlation function are clearly adding significant constraining power to our results. And with these, we hope to be constraining further real data. So we're going to apply this to the BOSS LRG sample, as well as eventually the DESI Bright Galaxy survey to try to actually improve the parameters constraints on our real data. So this is all work in progress. So if you have any feedback, I'd be really happy to hear it. Thanks very much.
Questions for Kate? Oh, Shirley, anyone, Boriana or Shirley?
Thank you. Yeah, super nice talk. One quick question is, have you tried this with redshift space distortions, or is this just in real space?
So this is redshift space, yeah. So all the mocks we put into redshift space, and so they're using that information to try to get these constraints. Yeah.
Okay, thank you. And for the assembly bias parameters in the HOD model, do you happen to remember how they play into the HOD?
You mean how exactly the assembly bias affects the HOD?
Yeah.
Yeah, I'm not sure if this answers your question, but a little more on the assembly bias model is what it basically does is sort of multiplies the HOD by a factor to move galaxies from low density to high density environments. So what we're doing with this like high FN parameter here that you're seeing is you're making it things much more strongly clustered if you have a low FN, I think it is, a negative FN, and then flipping it in the other way. So that's, yeah, we've used this simple 3-parameter model, but there's lots of other ways to parameterize it, and you could use the same approach on that as well.
All right, so you have a positive environment sort of measure there, or?
Yeah, so I think that negative FN ends up being moving things to that high density environment.
All right, that makes sense. Okay, thank you.
Shirley?
Okay, can I ask two questions? One is that what is limiting the error? Is it like the 2%? Is there some way to beat it if you just have more training set, or is there some like limit that you can't hit, or you just don't care beyond that 2%, right? And then the second question is for the mark correlation function. Like, do you tune it for the mark so that you actually maximize information for certain parameters? Thank you.
Yeah. So to your second question first, we spent a while choosing the parameters of the mark correlation function to kind of optimize for getting the biggest spread across our training set, so we would get more power from it. So that I didn't include this plot, but basically, yes, we tuned these parameters of the marked correlation function, the local density the sphere that we choose, and this rho, star, and p to have a larger spread in the training set, so it's more sensitive to different parameters. And that did end up making a difference in the final result. You remember what your first question was?
Is there anything to improve upon the 2%?
So yeah, you can see that in our emulator accuracy, we're still like significantly above the sample variance. It's a little bit confusing how we calculate the sample variance, because we actually calculate it on the test set because we have that the 5 realizations and we're comparing it to the training set. So it's possible that this actually is the best we can do despite that difference. But I think we could do better with kind of improved tuning and power in our models and a larger training set. The thing is, we're kind of limited by the cosmology spread. We can always add more HODs, and that we've found doesn't end up getting much better, going from 60 to 80 to 100 HODs for each of those 40 cosmologies improves it somewhat, but not that much. So that's something to try to keep going, but we are a bit limited by that.
Paco?
Yeah, so thank you. A very nice talk. So I was wondering, so how do you compute the covariance in this case?
So that is the thing that's been delaying this project by a year, is the covariance matrix that we compute is using the emulator performance, and that should incorporate both the error in the training set as well as the emulator error. We could also separate those by subtracting off the known error in the training set. Here, I'll go to the slide with the covariance matrices. But it's quite noisy because we have these, there's a large spread of parameters, and we only have a limited number of test sets. So on the left here is our original covariance matrix from this method, which is quite noisy. And so we thought it was causing some of the spurious modes we were getting in our posteriors. So what we did is what a previous paper had done as well, is done a basic Gaussian smoothing on this covariance matrix. And so you can get extremely smooth, which is smoothing out too much noise. So we chose just a Gaussian smoothing with a 1 sigma width, and that did help a lot. So this figuring out the covariance matrix was a big part of it. We also even tried like using other simulations with our emulator to try to figure out that spread. That didn't work as well as using our already pretty nice training set.
And if I can ask maybe a quick one. So have you tried to test if you know, all the machinery works now with a completely different simulation, you know, Illustris TNG or something with semi-analytics or?
Yeah, we ended up testing that in trying to make the covariance matrix. We used the GLAM simulations, which I think they were larger than ours, so we could test that variance more. It worked pretty well to predict the input parameters, which I was impressed by, but we haven't applied it to maybe more detailed ones such as TNG. That would be something to try. But the idea with all of this project is we've built these emulators for all these statistics, and in previous work we've done it for all these other statistics as well, halo bias, things like that, and they're like publicly available emulators that you should be able to just apply to your statistics, and they're pretty, or to your simulations, and they should be pretty accurate.
Chan?
So I have a question about following up on Paco's question about the covariance matrix. So these are derived from the Gaussian process itself. So is that correct?
They're just using the predictions of the Gaussian process. Actually, they're not taking advantage yet of the uncertainty that the Gaussian process gives you.
So you're drawing observables from your GP and then calculating the covariance matrix using that.
Yes, but we're using the our test set to do the sampling of those particular parameters and getting the predictions, and then using the error between that test and predictions to get this covariance matrix.
I see.
So we're not using just random sampling of the Gaussian process.
I see. And then in your actual analysis, are you somehow incorporating the 2% and 5% for the mark correlation function into the likelihood, for instance?
Yes. So then the likelihood includes the covariance matrix, which includes the error that you saw of the output of both the Gaussian process and the sample variance.
I see. Okay.
We add those together.
Thanks.
Okay. Yeah, one last question. Oliver?
Cool. Yeah, nice talk. One question I have kind of slightly more generally. Is there a nice way of combining these kind of Gaussian process emulation stuff with, like, say, standard linear theory on larger scales? Because it seems like the error bars are increasing towards large scales where we do know the theory pretty well.
Yeah, good point. So we do see that, these errors for certain statistics do increase a lot towards these large scales. I think that would be great. I don't have any expertise on how you might do that, but it does seem like Gaussian processes are a pretty robust way to work at these small scales, and then you could figure out how to kind of connect those with what we know about the large scales. But I'd like to work on that if you have more ideas about that too.
Okay, cool. Thanks very much.
Are there more questions? If not, let's thank Pete again. The next talk would be Agnes Perte on categorizing cosmological models with unsupervised learning.
Thank you. Hi, everyone. So I will talk about the work that I led in the past year to apply unsupervised learning to find our way in theory space with the amazing data that we will have in the coming decade. So beyond measuring the tensor to scalar ratio R with cosmic microwave background experiments, or measuring the dark energy equation of states W with large-scale structure experiments, we also want to test new physics. And when you break the standard model, there is actually a lot of freedom in theory space. For instance, for inflationary models, there is this whole suite of models as listed in the Inflationary Encyclopedia. If you're interested in tests of gravity, there are 4 different ways you can break general relativity, and that leads to a whole family of different theories of modified gravity. And on top of that, you have dark energy models, curvature, extra relativistic species that you want to test. In general, we parameterize those models, and then we measure the parameters to test if they are different from the standard model of cosmology. Now, in the case of weak lensing and clustering, for instance, as we do in DES, we go from the image of galaxies to summary statistics And so, for instance, in this case, the 2-point correlation function of the ellipticities of galaxies. And from that, we go to constraints on the cosmological parameters and these parameters of the extended models. And this step is very time-consuming and very computationally expensive, as we talked about earlier. First, because you need simulation to model the nonlinear scales that you want to take into account in your analysis. And when you do the posterior estimation using either MCMC or nested sampling, and I agree, in like 10 years, I don't think that's what we will use. But still, at the moment, this is takes a lot of time because the parameter space is more complicated, and the Boltzmann code is also takes longer at each likelihood evaluation. So here the question is it worth constraining all the models? Can we kind of optimize which explore new physics in an optimal way? And by the way, I'm in the non-Gaussian session, but I'm very much a 2-point function type of person. But you can imagine bispectrum instead of 2-point function here. This is applicable to a whole kind of models and observables. So the approach I propose is to use a dimensional reduction algorithm to simplify the theory space. So the idea is to map the models into a 2-dimensional space based on the impacts of these models on the observables of interest. And to do that, self-organizing maps are a perfect tool. So they help represent a multi-dimensional space into a low-dimension pixelized map. So you can see on the right a schematic view of what it does. If you were to train a self-organizing map on paintings, it would cluster kind of the paintings that look the most alike, for instance, that have faces in them and trees in them at the bottom right. So the closest pixel or neurons on the map would correspond to data that looks the most alike. So now imagine instead of paintings, you train the sum on cosmological parameters, and then you will be able to see which model overlap on this map, which will mean that this model has the same impact on the observable of interest, and that maybe you don't need to constrain both of these models. So in collaboration with Shubhanani and Dan Masters, who are specialists of using self-organizing map for photo-Z estimation, with my students, Bridget Momini and other cosmologists at JPL, we applied that to the case of modified gravity theories probed by cosmic shear. So we go from this space of modified gravity theories then to our observables, so the 2-point correlation function, psi plus and psi minus, as a cosmic shear, as a function of the angular scale between galaxies on the sky. And from there, we go to our self-organizing map. So as a first approach, just to show the idea of this approach, we take a pretty simple case. We fixed the cosmological parameters. We pick 3 different theories of modified gravity that have a cosmological impact. So F over gravity, the dialecton and symmetron models that kind of behave as a fifth force. And they are parameterized by the parameters here in this table. And then we select 100 values of these parameters within a prior range. From these parameters, we use the Cosmosis code using the MGChem Boltzmann code to compute this cosmic shear 2-point correlation function, psi plus and psi minus. And we use 10 redshift bins because that's what we expect with LSST, for instance, or Euclid. We select a part of the range of the angular separation, theta, for psi plus and psi minus. And in the end, we flatten this data set, and we end up with something that have 45,000 elements. And then we use the SumPy Python package to produce a 6x6 pixel self-organizing map grid. And to tell how alike two models are, we use the Euclidean distance metric. So in the end, we have a total of 500 models. So we train our self-organizing map on those models. So the way it worked, just briefly, is the grid of neuron is shown the input data, and each point of the grid will be weighted, strongly weighted if it's closest to the input data, and less weighted if it's further away. And then we repeat the process until the grid describes the input data well. So in our case, we initialized the grid with the principal components, and we needed 3 epochs to finalize the training. And this is what we got. So this is showing the pixelized self-organizing map, where we color each pixel by the number of models lying in each neuron. So a lot of the model actually lie in this one cell that corresponds to general relativity or small deviation to general relativity. And then you see other cells are also populated, and I will show you what it corresponds to just after. But to give you an idea of what this means is that in the cell 2, for instance, corresponds to the cosmic shear correlation function shown here on the right in purple. And cell 3 shows the one in blue. So you see they have a different kind of trends. And that's what the self-organizing map is picking up and placing this data accordingly. So now we can also color this self-organizing map by the value of the parameter in each theory. And that tells us how those theory compares in terms of cosmic shear. So first of all of the theories kind of live in this top left part. So that means that that actually corresponds to small values of these parameters. So basically for the small values of modified gravity parameters, they have the same type of impact on cosmic shear. But then you see that for the Dynamical model, it's lying on the top part only, which and this top right part is not overlapping with any cell from the F of R or the symmetron model. So that means that if you were to only constrain F of R gravity with cosmic shear, then you would miss some information that you would get if you were also testing the Dynamical model. And then we also wanted to see how does that compare to a dynamical dark energy that is often parameterized as W0 WA. So we compute the cosmic shear for a different combination of W0 WA and map that on the self-organizing map trained on modified gravity. And we see that a lot of the model are relying only on 2 cells, these 2 cells on the top and the bottom. And that means that there is actually a very different information when you're looking at dynamical dark energy. And so it's not enough to just look at that when you have large-scale structure experiments, because you're missing a lot of information you could get if you test gravity. So this is our first study. And the next step is to see how actually if you measure the cosmic shear, how does that impact your ability to distinguish between different modified gravity theories. And for this case, we would compute the chi-square per cell in the self-organizing map, given a fiducial data vector. And that will kind of lead to a type of contour plots, and we will be able to tell, okay, with this covariance matrix, I'm able to separate between F of R gravity and the Dynamical model, for instance. And we can also use this approach to see the impact of systematic errors or nonlinearities on our ability to distinguish between these theories. But of course, this is applicable to a lot of observables and a lot of different other studies and cosmological models you're interested in. And the application is to see again which models are overlapping, have the same impacts on your observable, or even which parts of the theory space you are missing and that you should go explore because you don't cover it with your current set of models to test. And you can also use this map to easily map out your measurements on it and see what type of theories it corresponds to. So this is the first step in this approach, and we have many next steps planned. So I hope this interests you, and happy to hear about your feedback as well. Thank you.
Questions for Agnes? Vanessa?
I'm a little bit curious about the self-organizing map. You might, I don't know, I'm not sure. It might be a little bit of a special question, but what's the advantage of self-organizing maps versus like other dimensionality reduction tools and then running a clustering algorithm on top of that, like UMAP or TSNE, for example?
Yes, actually. So it's just that. So in our case, we use self-organizing map, but instead of that, you could also use UMAP, which would tells you, which would give you information about the actual distance between the models. And that's actually something I want to do to compare the modified gravity theories and the dark energy models, because that will tell us like how actually far it is. This is kind of telling us how different it is, but not how far it is. So it's more like we would use it instead of using the sum. Yeah.
That would be interesting. Yeah.
Okay. Yeah. Thanks.
Any more questions? Paco?
Yeah, and also not very familiar with these things. So do you need the data to be like one-dimensional vector, or can you work with three-dimensional or four-dimensional data?
So in our case, we flatten our data to have just like one-dimensional data vector. But like for self-organizing map, you can give it anything, I think. But the package that we use, I don't think it can. For instance, it cannot take images in inputs. But I think self-organizing map can use image and even self-organizing map as inputs. So, yeah.
Any questions from the online audience? If not, let's thank Agnes again.
Thank you.
Next speaker will be Colin Hill, who will talk about non-Gaussian information in CMB secondary anisotropies.
All right. Jay, do I just change with this?
Yeah.
All right, great. Okay, so I'm going to talk about this sort of broad-sounding topic of non-Gaussian information in CMB secondaries. Mostly going to focus on the thermalized Z effect here. So this is a line of research that goes back several years now, I guess, mostly with Kendrick Smith, who's down here on the right from Perimeter Institute, and then more recently we were joined up with by Leander Thiel, who's a grad student in Princeton, who I think we'll see here at the workshop later in the week. All right, so first I just want to remind people that we think of the CMB as a Gaussian random field, but the analysis of non-Gaussian statistics in the CMB is now a routine subject. So just going through a couple of examples quickly. First of all, CMB lensing reconstruction. When we look at the power spectrum of a reconstructed CMB lensing convergence map, that's a 4-point function of the CMB temperature and or E-mode fields. We're very used to seeing that. We've now measured the kinematic Sineyev-Zeldovich effect through cross correlations with large-scale structure tracers. All of those are actually also non-Gaussian statistics. They're 3-point functions. either of the form TTG, where T is the CMB temperature and G is a galaxy tracer or other large-scale structure tracer, or of the form TGG. This is an example of the former class in a paper led by my student Ola Kuziak that was just published in PRD, where we measured the KZ effect through cross correlation of this form with Planck data and data from the WISE satellite. And Simone was also involved in this work. And then lastly, the thermal Sinyaev-Zeldovich effect. There have been robust detectors now of multiple higher order statistics of the TSE field. I'm going to talk about the example here on the left involving the 1-point function for most of the next part of the talk. There's also been measurements of the bispectrum, for example, seen here on the right from the South Pole Telescope, where the 95 gigahertz, 150 gigahertz, and 220 gigahertz millimeter wave sky was decomposed into its contributions from the TSZ and other secondary fields, such that they could extract the TSZ bispectrum. And similar exercises have been done by the Planck collaboration as well. All right, so let's turn to the subject of the TSZ field. So we've seen examples of weak lensing maps earlier, which have similar structures to this. And I think it's very convincingly argued that we need to go beyond the power spectrum to extract all the information in such maps. This is a map of the Compton Y field, the dimensionless quantity that characterizes the TSZ signal. And you can see that this is a log scale on the right, so it's very much weighted towards the location of massive clusters and groups of galaxies. It's a highly non-Gaussian field. I should say this is from a hydro simulation run by Nick Battaglia at Cornell. All right, so just a lightning reminder in case people aren't familiar with the TSZ effect. This is the change in the temperature of CMB photons as the inverse Compton scatter off of hot electrons, most of which are located in the ICM of galaxy clusters. And so this dimensionless quantity I was talking about, the Compton Y field, is this particular integral of the electron pressure on the line of sight multiplied by some factors that make it dimensionless. And then has this frequency dependence in front, G nu, which is very unique, shown here. So you start with some initial blackbody distribution of photons. It gets upscattered to higher energies. That's what's shown here on the left. If you look at it in terms of the delta intensity on the right, you can see this famous spectral function where you have a decrement below 218 gigahertz and an increment in CMB temperature above 218 gigahertz. So most of the talk will either talk about the Compton Y field, which is frequency independent, or the TSZ field at 150 gigahertz, where it's a decrement. All right, so the main statistic I'm going to talk about in terms of non-Gaussian statistics is the 1-point PDF. So this is, I will argue, is an optimal statistic for the TSZ field in particular. So some of the general advantages of this statistic are that it's very easy to measure. It's a histogram of the pixels in your map. It captures the information, all the zero lag moments of the field. And in fact, we heard earlier, it actually captures information for a non-Gaussian distribution that's beyond that contained in all the moments. In terms of thinking about this for clusters, it's great because you don't have to model the selection function of some particular objects. We're not making a catalog of objects at any point. As I'll show you in a second, we've developed a fully analytic model of this signal. It's quite accurate. And then lastly, I think this is specific to the TSZ, but it's the near optimal cosmological statistic for fields whose parameter dependence is primarily due to their sensitivity to the halo mass function. So the TSZ field is very much just Poissonian. There's very little information in the clustering in that field. The dependence on cosmological parameters really just comes in through seeing some projection of the halo mass function, which is sensitive to sigma 8, omega m, neutrino masses, and so on. So in terms of data, I showed you this a minute ago. This is the 148 gigahertz map from the original ACT survey, now 10 years ago, where we see this tail of decrements down to negative values. That's the TSZ signal. And to confirm that, you can look at 218 gigahertz, the null of the TSZ, and see that there is no similar tail there. Okay, so let me walk you through our analytic model for this signal very quickly because I think it's quite nice. Then I'll talk about some more recent developments. So the conceptual way to think about the Finalized PDF or any PDF like this is that you're just asking how much sky area is subtended by particular, in this case, Compton Y values in some given range. So if the sky consisted of a single cluster, it's a trivial calculation. You're just calculating the area between two circles like this, the area in this annulus for a spherical cluster anyway. If the clusters never overlapped, then the full calculation is just summing up the usual integral over the mass function for all the clusters in the universe. Obviously, things are more complicated in real life. There's non-thermal LZ contributions to the CMB map. The noise properties are also non-trivial. When we applied this to actual ACT data in 2014, we took those things into account very carefully. But I want to talk about theoretical developments in the last couple of years, which are these 2 points I've highlighted, involving the treatment of cluster overlaps and then the clustering of clusters. And these were the developments that we worked out when Leander joined up. So the way to think about the first issue, how to think about clusters that overlap in projection, is to actually realize that everything gets simple if we go into the Fourier conjugate space of the PDF. So imagine taking the Compton Y field, dividing it into redshift shells, as I've written up here. If the Compton Y field is uncorrelated across the shells, then the final P of Y that you observe is just the convolution of all the individual PDFs, because you just have the sum of a bunch of random variables. So you can perform a similar operation, dividing it up into infinitesimal bins in mass, and then you get this, this convolution. And when you see a convolution of an infinite number of things, that tells you that you should have been working in Fourier space, where everything becomes a multiplication. So that's what we did. We translated this formalism into the Fourier conjugate space of the PDF, which is represented by this P tilde of lambda. And then I skipped the derivation here, but the result in the case where you neglect clustering is this expression here. So this is an exact result in the halo model, in the same way that we have the classic results for the one halo term in the power spectrum, or the two halo term in the power spectrum. This is the exact result for the 1 point PDF, where basically looks like an exponential of this integral over the mass function times some function of the profiles of the objects, which are captured in the Y naught up in the right-hand corner there. So it's pretty straightforward. And then accounting for the clustering is a little bit more complicated, but still tractable analytically. The reason this matters is that clustering increases the probability that you're going to get overlaps along the line of sight. If you're looking at the three-dimensional voxel PDF, assuming that you enforced halo exclusion, then the two halo term would be irrelevant. It's just a one halo calculation. So it's really the line of sight projection that leads to this effect. And I'm not going to walk you through the math, but it turns out that you just get this additional exponential factor, which looks, as expected, like a Limber type integral over the linear power spectrum. So again, this is an exact result in the halo model. All right, so how does this actually end up mattering? So here's a calculation of the thermal LZ PDF using this analytic method, which is labeled fiducial result. A calculation, sorry, these are all using the analytic method, sorry. Fiducial result, which was without accounting for the overlaps or clustering, sorry, including the overlaps clustering. The blue is without, and the red is including the overlaps but not clustering. So the dominant difference, which is shown in the bottom here, in terms of the residual, comes from, in this case, the inclusion of the overlap effect, which is important at the level of tens of % for the thermal LZ field. The clustering turns out not to matter very much, but for the weak lensing case, which we later turned to, accounting for clustering is also important. So then we compared to simulations. So now the black curve is the analytic result. The dashed red curve is what we call simplified simulations, where we just throw down a bunch of clusters in a Poisson distributed fashion. So those can be generated ab initio very quickly. And then the blue is full hydrodynamic simulations, in fact, the ones I showed you a picture of earlier. So we get a nice match here with the analytic method. The hydrosims turn out to be incomplete in the mass function as you go down to low masses. And we showed in the paper that that discrepancy you see as you go towards the peak of the PDF, which is only at the level of 5% or 10%, is just due to the incompleteness in the mass function in the hydro simulations. So the formalism seems to work quite well. One nice thing about having the analytic model is that you can look at parameter dependence or study contributions to the PDF from various mass and redshift ranges, which we did in this paper. Here's the parameter dependence. So you can see it's quite sensitive to sigma 8, as expected, because we're looking at basically a projection of the halo mass function in the exponential tail. It's also sensitive to omega m and has some sensitivity to the neutrino mass as well. Of course, we're looking at gastrophysical observables, so it's sensitive to the parameters describing the pressure profile. But one nice thing is that this has a significant enough difference in sort of the parameter dependence that you can break the degeneracies between gastrophysics and cosmology. All right, let me maybe skip this, just quickly say that we showed explicitly in this paper that these improvements in the analytic model were sufficiently large that they would need to be taken into account for PDF analysis with upcoming Compton Y maps from the Simons Observatory. All right, so now here at the end, let me first talk about weak lensing and then talk about what we've been up to since these papers came out. So in one line, you can say, how do you translate this to the weak lensing convergence PDF? And it's just replace Compton Y with weak lensing kappa and all those equations I showed you. It turned out to be a little harder than that. Took us a little while to get this to work, but eventually we did. And that was the second paper with Leander down here. We're comparing a similar analytic model to what I just showed you to the massive news simulations that we saw earlier from Jielu and others, including me. So these are different redshift slices where you're seeing the analytic calculations in red and the simulations in black. The match is very nice. After we realized that we needed to account for basically the finite resolution of the simulations, which we obtained by matching at the power spectrum level. So the finite resolution of the simulations leads to these smoothed analytic curves, the dashed red curves, which then match the simulations very nicely. So this whole formalism really does work for a number of different cosmological observables. All right, so then the last thing you want to do after you have some nice analytic model of some cool non-Gaussian observable is to constrain parameters with it. And this is the remaining thing that I think we don't know the answer to. Kendrick and I have thought about this for years, off and on. We don't think that this likelihood function is actually tractable for the PDF observable. What it looks like is basically a Poissonian, basically a Poisson distributed observable for which the likelihood function should be the cache statistic, which people from the cluster world will recognize. But in this case, the bins have arbitrary correlations amongst them. So in the PDF that I showed you earlier, you can imagine you have a single cluster that contributes both to bins near the peak of the PDF, as well as to bins that are further out in the tail, which leads to complicated correlations across bins. But the counts in each individual bin follow a Poisson likelihood. We haven't been able to really solve how to do this. So you could try just assuming a naive Gaussian likelihood where you have some covariance matrix, assume that the bin counts are Gaussian distributed. That turns out to yield biased parameter inference, which you can show even with older CMB data. So this was work that I did at the ACT analysis several years ago, and what I did was just run a bunch of simulations through our pipeline, assuming a naive Gaussian likelihood. And as you can see, the distribution of the recovered values of either sigma 8 or this gas physics parameter P naught are biased from their input values. And what we did was to basically Gaussianize this observable by just chunking a bunch of the bins together so that the counts were then Gaussian distributed instead of Poisson distributed. But you lose information when you do that because you're losing some information about the shape of the distribution. So the opportunity here then is that this seems like a perfect setting with which to demonstrate the utility of likelihood-free inference, where you don't have to know what the likelihood function is, and that's what we've been working on more recently. So as I'd mentioned, we have this simple simulation code where we just throw down a bunch of Poisson distributed clusters. We can generate huge numbers of simulations easily, and that type of modeling probably suffices for upcoming experiments. So what we're doing now is basically coupling this to the Delphi code that we heard about earlier. So here's some very preliminary results that'll just flash up at the end. So first, this is what you get if you do a naive MCMC, assuming a Gaussian likelihood. This is now a 3-parameter model with sigma 8, omega m, and this gas physics parameter P naught. And here you can see the bias cropping up that I showed you a minute ago, in this case on omega m. So, okay, we're seeing a bias as expected. Now let's try using LFI. Indeed, the bias now seems to be eliminated. We get posteriors that more or less are centered on the input values. The sigma 8 one looks a little bit weird. But it doesn't seem to be quite as constraining as we were expecting based on, say, a Fisher calculation. So that's why this is labeled extremely preliminary. I say Leander is the one leading this work, but I'm optimistic that this is a nice test case to show what you can do with LFI when you don't actually know the likelihood function of your observable. All right, so let me just wrap up. Hopefully I convinced you we have this very cool analytic model for this non-Gaussian statistic, which is kind of a unique thing to have. It's very accurate for thermal SZ and also works quite well for the weak lensing convergence field. We're trying to solve this problem with the likelihood function. As a reminder, why we're doing this, in case it wasn't obvious, it's that we want to tighten up constraints on sigma 8, possibly neutrino mass, and certainly cluster astrophysics parameters. So the usual arguments for using higher order statistics. And then lastly, the longer term goal for this work, I would say, is to try to model non-TSZ signals in these simulated maps simultaneously with the TSZ and just LFI everything. When we first talked about this with Stephen Feeney and Justin Elsting, they immediately jumped to saying that that's what we should do. I suggested that we take a little bit of a more conservative approach first, but that's ultimately where we're headed. So I'll stop there and take questions. Thank you.
It's great as usual, but I have two related questions. One is, you said the variance in each bin of the PDF is Poisson. So did they check that against the simulations?
Yeah, so all I mean basically is just that imagine you only had a single bin of the PDF as your observable. Yeah. Very similar to like the cluster counts, right? Yeah. Some mass and redshift bins.
But in the cluster case,
that follows a Poisson distribution. Yeah. But the challenge is that here you have a whole bunch of bins, each of which follows a Poisson distribution, but they're also correlated in a complex, arbitrary way. And that, yeah.
I thought in the cluster case there is sample, correlations do matter.
So what we found when we looked into the literature on that topic is that people end up approximating that likelihood as Gaussian when you account for that sample variance term. Which I'm actually not sure if that's completely accurate. Nick and I were talking about this last year.
Then the related second question, have you thought about some intermediate to get the likelihood or the covariances? Just put random circles, Monte Carlo, some random circles, and measure the covariance.
So it's not so much that we don't know what the covariance is. Like we can actually calculate the covariance of the PDF analytically as well. That's in the second paper with Leander. The problem is just that even given the covariance of the PDF bin counts, it turns out that's not a sufficient amount of information to compute the likelihood function accurately. You actually need to know moments beyond the second in order to compute the likelihood for this observable. So that's why we think LFI is the way to go, probably. Yeah.
Okay, thanks.
Any other questions? Shirley?
The LFI version, like, do you imagine you doing like sort of postage stamp style, or do you want to do like the whole field?
Yeah, all the tests that we're doing are sort of postage stamp-ish. They're on, I think, few degree sized simulated maps. Eventually, though, yeah, we'd want to do it on maps that are as large as the ACT or SO maps. Yeah, I think that's further down the line. I mean, I'll be super excited if we can actually get an exercise like this to work out in such a way that the LFI-based posteriors match, what we expect from, say, a Fisher calculation and don't exhibit any bias. I mean, this would be a case where LFI actually solves a problem that we don't know the answer to in advance, which I would be very excited to see that happen.
If there are no more questions, we can thank Colin again.
All right, thank you.
The next speaker would be Louisa Lucy Smith. She'll be talking about deep learning insights into dark matter halo formation. Please take it away.
Can you see my screen? Hello?
1 second. Yeah, we can't see your slides on the main
slides yet.
Oh.
On the Zoom, it has shared the screen, but not on. Okay.
Let me try again. You still can't see it?
No, still not in the auditorium.
On Zoom?
Yeah.
Maybe I should stop video or. Is it definitely connected properly? Weird.
It's weird. It is working on Zoom, but it's just not working in the auditorium.
Let me just try. You still can't see it?
No. Sorry.
Stand by 1 second, Louisa. Go ahead and continue sharing your screen. We'll get it up for you.
Okay. Shall I stop sharing? Because
Louisa, can you share your screen one more time?
Yep. I am sharing it.
All right, 1 second. Hold it right there, please. All right, you are all set.
Okay, perfect. Try to share video. I don't know if you can see me, but. Okay, should I start?
Yeah, please go ahead.
Okay, sorry everyone for the technical problem. Hi, I'm Louisa Lucy Smith, and I'm a postdoc at the Max Planck Institute for Astrophysics in Germany. I'm very sad not to be there in person, but hopefully there'll be another workshop like this in person soon. Okay, so today I'll be talking a bit about what we've been trying to do with deep learning is to try and understand a bit more about cosmological structure formation. So as you all know, today's large-scale structure is basically a rich network of dark matter halos and filaments are surrounded by empty voids, which all originate from tiny perturbations in the density of matter early times. So what I'm interested in is to try to build a physical model of structure formation. So how can we build a model that maps these small linear density perturbations at early times in today's rich, complex network of large-scale structure, and answer questions like how do properties of large-scale structure emerge from these early times perturbations. So what I've been focusing on in particular is dark matter halos. So the most accurate method that we have to model the formation of dark matter halos is really through n-body simulations. So in n-body simulations, you start from early times when the density fields can be very well approximated by a Gaussian random field, and then you evolve that through just the equations of gravity, and then you obtain this highly nonlinear density field where the largest overdense regions are what we call dark matter halos. But really the most widely accepted physical picture that we have of halo formation comes from analytic models. And the problem is that due to the fact that the complexity of this model is limited by the fact that they need to be solved analytically, they can only provide qualitative understanding of how halos form. So what we've been trying to do is to see whether we can use machine learning to learn the mapping between the initial conditions and the final dark matter halos in n-body simulations, and use this mapping not so much as an alternative to n-body simulations or n-body surrogates, but to actually try to understand more about how dark matter halos form. So to try to gain insights into the physics of halo formation. So what we did in this work here is to turn the problem of halo formation to a deep learning model. So as I said, with n-body simulations, you start off from the initial conditions, which are typically the realization of a Gaussian density field at early times. And then, as I said, in the n-body simulation, you evolve it just using the equations of gravity, and then you get at redshift 0 a whole range of halos where you can extract their properties and learn about the structures that formed. So in this case, we focused on halo masses, but this approach can be used for different halo properties. And so what we did is to take the same inputs that we use for the n-body simulations and feed that to a 3D convolutional neural network, because the inputs are inherently 3D, and then predict the final mass of the dark matter halos that result from the simulations. So basically, instead of the whole n-body simulations, we want to go from the initial conditions density field to the predicted final halo masses via a 3D convolutional neural network. Now, of course, for a single simulation, for single initial conditions realizations, you have many different halos and many different halo masses. So to create this mapping between the initial conditions and the final halo mass, we do this basically for every particle in the simulations. So at redshift 0, we pick all the particles that end up in a certain halo. We trace back its location, the location of that particle in the initial conditions, and then we use as inputs the initial density field centered on that particle positions. So the input to the CNN is basically a sub-box of the full initial condition simulations centered on the particle position. And then the output is the mass of the halo to which that particle belongs at redshift 0. And so you can then repeat this for all different particles that are in different halos for many different simulations. And so you can then train your network to predict the final mass of the halo to which a certain particle will belong, starting from the initial density field in some sub-box around that given particle. And so by training the network on many different particles across many simulations, the model learns to predict what aspects of the initial perturbations, the initial density field, will be relevant to predict the final mass of the halo where these particles will end up in at redshift 0. So our model is actually a fairly simple model, compared to all the complex neural network and deep learning models that there are. It's just a simple convolutional neural network, which has many different convolutional layers and pooling layers, and then a couple of dense layers at the end to make the final predictions. And the question is, well, why do we want to use convolutional neural networks and not other machine learning methods? And the real advantage of these models is that they don't require featureization. So with more standard machine learning models, you always need to create some features from your data that then you use to as input to your model. But in this case, it's really the CNN that learns directly from the initial conditions, raw data, what are the features that are relevant to predict halo mass. And this is exactly what we wanted to use the network for, is to understand what properties, what features of the initial conditions density field are relevant to establish final halo masses. Now, the disadvantages of these kinds of models is that deep learning algorithms are known as black box algorithms. So if our aim is to understand what aspects of the inputs is the CNN learning, how can we do that if these models are black box algorithms? So the question is, how do we extract physical knowledge from a deep learning algorithm if it's hard to interpret? So we used a really simple interpretability technique that allowed us to understand what information of the inputs was the CNN learning to predict final halo masses. So the technique is simply to remove part of the information carried by the inputs and then retrain the model to measure the resulting change in the model's performance. So you take your raw inputs, you remove part of that information, retrain the model, and then the resulting change in the performance of the model will tell you how relevant the information that you removed was in the first place. So in this case, we wanted to test the role of anisotropic information in the initial density field. So we wanted to know what happens when you remove anisotropic information from the initial density field. So to do so, we just took all our input 3D boxes and just computed the mean density over shells around the center. So remember that the center is the particle's position. So to remove anisotropic information about the density surrounding that particle, we just take the mean density in shells within that sub-box. And so in this case, we have two models, one that uses the full information of the initial density field, and the other that only uses this average density information. So then with the two models, as I said, we compared the predictions of the two models. And this is what is shown here in these three panels. So the three panels are basically halos of different mass ranges. And the two histograms are the residuals in the predictions, one from the raw density case, so the model trained on the full information in the inputs, and the other model trained on the average density input, so only information about the mean density over shells around that particle. And basically these two histograms look fairly similar. We've done model comparison using various metrics, and we find that the two models are consistent. So what this means is that the anisotropic information in the initial density field plays very little role in establishing final halo masses, or that the features that the CNN is learning in the first place are equivalent to spherical averages over the initial density field. So in this work, we specifically wanted to test a certain hypothesis, which was, what is the role of anisotropic information in establishing final halo masses? And the question is, can we go beyond that and actually try to develop interpretability techniques that allow you to learn new things about the physics of structure formation without having to formulate a hypothesis in the first place? So this is what we're trying to do in our current work, where we're basically borrowing some ingredients from autoencoders, but using them in a supervised setting. So in this setting here, what we're trying to do is to predict the radial profile, the radial density profile of a halo, starting from the density field at redshift 0 that is surrounding, so a sub-box surrounding the halo. So the idea of this network is to have a first part of the network that is basically the encoder, so that you try to compress the information about, in this case, the halo's inner structure into a simpler, lower dimensional representation, like a latent representation, like in the case of variational autoencoders. And then the second part of the network is a decoder, which tries to answer the question, what is the density at a given radius? So this is what we do, for example, when we have an NFW density profile, when you have a functional form for the profile, and then you can establish what is the value of the density at a given radius. And so the aim is to have this bottleneck here, this lower dimensional representation that compresses the information about the halo's inner structure. And so the decoder then makes its predictions only based on this representation. So if the bottleneck does encode information about the halo's inner structure, then it should be able to make predictions about the density at any given radius. So for this reason, we add an additional input to the decoder that is in fact the value of the radius at which you want the density to be evaluated. So the aim of this project is then to interpret what physical parameters does this bottleneck encode. What is the physics that is encoded in here that describes, that parameterizes the density profile of a halo? So we're basically trying to use the dimensional reduction technique to extract knowledge from the neural network about a given problem that in this case is the density profile. So let me just conclude saying that we've developed an interpretable deep learning framework that allowed us to establish the role of anisotropic information in the initial conditions in establishing final halo masses. And we're now trying to go beyond this and develop this supervised variational encoder to try to extract new knowledge from this bottleneck by interpreting it with respect to physical parameters. And I'm also working on future applications on different halo properties and other cosmic structures like voids. Thank you very much, and I'm open to any questions.
Questions for Louisa?
Oh, hi. Thanks for the talk. I had a quick question about the autoencoder. In your case, what is the loss function? So since usually it's just the reconstruction loss, but in this case, you have the density profile.
Right, exactly. So in this case, the loss function is just the mean squared error for the prediction, the final prediction. So you have, in your training set, you have the true density profile and the predicted one. So you can just compute the mean squared error there. And then you have a term that basically is the KL divergence between your prior of your latent variables and the predicted ones. So this is the same KL divergence term that you have in variational autoencoders. It's just that instead of the reconstruction loss, you have the mean squared error.
I see. Okay, thank you.
Thanks for the interesting talk. So can we go back to the previous slide showing the histogram of reconstruct mass predictions? So it seems the prediction is not perfect, right? So and you said the input is already the surrounding, the neighborhood of the particle. So I wonder whether this imperfection of prediction is due to the physics outside the box of your input of the network, or that's because of the limitation of CNN, for example. It's not extracting really all the relevant information.
Right. So actually, the reason why the predictions have a largish error is not because the neural network can't extract the information, it's just because it is extracting spherical averages over the density field. So from analytic models, we know that the predictions coming from spherical collapse models are consistent with the one of the CNN. The information that the CNN is missing is all the information about the gravitational evolution. So we're only giving it initial conditions to final halo mass. So what it's trying to learn is just an effective mapping between what properties of the initial conditions can give you back the mass of a halo. So what
okay,
is...
so the input is only the density field, right? It's not including velocities, or it also have velocity information?
Well, it's only the density fields, but in the linear regime, those are related. So actually the CNN can they're related by convolutions even. So the CNN can actually extract one from the other. So again, that's not the problem. It's just that you're just giving it the initial conditions, the initial part, and the final halo mass. And what it doesn't know is the whole gravitational evolution that maps one to the other. So we're
but I would, sorry. Yeah, but I would guess if you have the initial condition and the process is deterministic, so in principle, you should have a very concrete answer for the final mass. but we see this dispersion of prediction. So I wonder whether that's because the input is not enough really to tell the mass, or it's because the CNN is losing some relevant information. Like given the initial condition, we should in principle, I mean the physics is deterministic, right? So there's only one corresponding final mass. I would guess.
I guess it depends what you mean by information, right? I mean, the initial conditions contain all the information in entropy sense, right? But there's also information in the model. If you think about it in a Bayesian sense, there is information in the model, whereas the CNN doesn't know anything about how gravity works. So if you gave it an information about how gravity works in terms of a time evolution, then it would learn some model that could resemble gravity. But in this case, it's only really learning an effective mapping between some features of the environment around the particle and halo mass, and that has nothing to do with gravitational evolution in the way we mean it through an n-body simulation.
Okay, thank you.
Yeah.
Sultan.
Related questions is how does these errors shown on your screen compare to the spherical models, the peak patch, for example, which are deterministically telling you for each initial particle how much is the halo mass it's incorporated?
Yes.
So is this much better or much worse or similar?
No, they are consistent, which is expected actually, which was another validation of the fact that the CNN was learning something like spherical averages, because the error in the predictions are what we expect from analytical models. So they're consistent.
So if you plot these distributions in, let's say, peak patch model, it looks similar?
Yeah, so I tested against EPS and Chef-Torman, not specifically peak patch. But for those two cases, then they were consistent.
I see. I guess that makes sense if your anisotropic information is almost negligible.
Exactly. I mean, if the predictions were much better, then it would have meant that it was learning something else that we weren't seeing.
So I have another neural network input-output question. I just didn't fully follow. For your initial CNN that you're showing on this slide, but the architecture is like 2 slides above, I think, or
this one?
Or 1 slide below. Yeah. So basically, I see a cube going in and I see a value coming out. And I'm wondering how you then predict multiple values. Is that cube that you're putting in, is that a sort of subcube of your data, or is it the whole data cube?
Yeah, no, exactly. It's a subcube of the data. So it's basically, yeah.
So then you're convolving that whole thing over the big cube.
I'm convolving the
or are you extracting subcubes from this and always predicting the value of the middle voxel of the
right, exactly. So maybe it's easier to see in this panel, in the top panel here. So essentially the input is the sub box around a given particle.
Okay.
So it's some sub box, so like, cut out from the full initial conditions. And then the output is the mass of the halo where that particle ends up in. So then
Okay, I think I understand. So basically, like I was a bit confused because there was a, there's a fully connected layer at the end, but the fully connected layer is basically just convolutional layer where the filter size is the same size as your data, and then you could move the whole thing over your data, and then it would be like a perfectly convolutional network. That's the thing that I didn't get, but like now I think I understand.
Yeah, I mean, you can use the fully connected layers are just there to basically assemble the features that were extracted in the convolutional layers into one number, which is the mass prediction. But you can replace these fully connected layers with other layers that similarly would give you a one number.
Yeah, thanks.
Yeah.
I think Abhi had a question.
Thanks for the talk. It seems a bit counterintuitive to me that the anisotropic information does not really matter to get the halo mass. But do you think if you add the gravitational information as well on top of just the initial density field, then the conclusion might be different? Because ultimately the halos are made through accretions and mergers, and that should somehow depend on its environment, right?
Yeah, so I think the point is that the conclusion is specific to halo mass. So I'm not sure if adding gravitational evolution information would give a signal for tidal shear, but it could be that for different halo properties, such as, you know, the halo concentration or a different halo property, then anisotropic information is important. So the point is that the conclusions about halo mass, but it doesn't mean that anisotropic information has no role in structure information at all. Like, obviously that can't be the case, but it could be for a different property of halos or galaxies, then you do find the signal in the tidal shear. But in this case, we don't for halo mass.
Sultan?
So I want to ask, so also for the training set, so each depending on how the number of particles in each halo, right? So like if you center around the particle, then it means that if you require only less 20 particles, then there is 20 cubes correspond to a single halo mass output. Is that correct?
Yeah, that's correct.
So my question is that, does the result depend on the number of particles that you assume to resolve halos, and whether the size of the subcube that you assume affect the result? How do you specify these things, or did you look how the accuracy changes with the number of particles, like the minimum number of particles to resolve halos, and also the size of the subcubes?
Yeah, so just like in the simulations, I mean, halos that have very little number of particles are not very well resolved. So we basically only pick halos that have at least 100 particles in them, and we find those to have reliable predictions. In terms of the size of the subbox, of course, that's very important because you want to include you know, scales as large as they matter, right? So if you pick a subbox that is too small, then you miss out large scale information that are relevant, for example, for high mass halos. So we basically tested this empirically by picking larger and larger subboxes until we found that the predictions converged, meaning that we had a large enough subbox to include the most relevant scales.
And so then you assumed, like, if you say 100 particles, then you assume that like 100 different boxes in order just to get more data, because you could also imagine the case where you just have like a big box which includes all the particles together, right? Like the halo center within a subcube, not like for the 100 subcubes for each particle, right?
Right. Yeah, that would be equivalent to just doing the mapping for the center of the halo.
Okay, right, okay, cool. Yeah. Thanks.
Is it a quick question? Okay, go ahead.
whether you got a chance to look at the kernels in the convolutional neural net learned, whether there are any interesting patterns in the kernels.
Yeah, I did have a look and I couldn't see anything. I tried a lot of these visualization techniques and yeah, they were just pixels. I mean, yeah, they weren't very useful to me. Yeah.
Okay, that's quite common.
Yeah, exactly.